video, I'll be going over section B of practice paper set 1 OCR physics A, and this is I've already done section A of this paper. I will put a link down below as well. So let's get started with question number 16, which says that a battery is connected in series with a lamp and a resistor, and the battery has an EMF of 6 volts and a negligible internal resistance. Potential difference across the lamp is 2.4 volts, and it dissipates 60 milliwatts of power. The resistor has a cross-sectional area of 2 millimeters squared, and the number density is also provided to us. So we need to calculate the resistance R of the resistor. So we can work out the resistance by using V over I, and the voltage across the resistor is just 6 minus 2.4, which is 3.6 volts, okay? And for the current, we can use the information from the bulb, okay? So the bulb is, current is equal to power divided by voltage, okay? So the current across the bulb, which is the same as the across the resistor, will be 0.06 over the voltage, which is 2.4, which gives me 0.025 amps. And therefore the resistance now can be worked out as simply 3.6 volts over 0.025, and this gives me an answer of 144 ohms. And because everything is rounded to two significant figures, it will be 140 ohms. For part B, we are asked to calculate the mean drift velocity V of the free electrons within the resistor. So we know the equation I is equal to NAE V, therefore V is equal to I over NAE. Current is 0.025. The number density is 1.4 times 10 to the 25 per meter cube, and the area is given to us in millimeters squared, so I am gonna just times it by -3 squared, okay, and that would be in meters squared, and the electron charge is this much. So that gives us an answer of 5.6 times 10 to the -3 meters per second. So for the next part of the question, it says the number density of the free electrons in the connecting wires is greater than the resistor. The connecting wires have the same diameter as the resistor, and state and explain whether the mean drift velocity of the free electrons would be smaller, the same, or larger than your value in part B. So, well, if the number density is greater, we know that V, okay, according to the formula, is inversely proportional to N. Okay, so since V is inversely proportional to N, okay, this would basically reduce the mean drift velocity. Okay, V will be lower. Okay, so let's move on to part D. A student connects the circuit shown to plot an IV characteristic graph, okay, of the filament lamp, and we are given that the current in the lamp is I, V is the potential difference, the supply has an EMF of 2.4 volts with a negligible internal resistance. The maximum resistance of the variable resistor is 60 ohms. Explain why the circuit will provide data for large values of V, but not small. Okay, so we have to think about two different situations, and that is when the variable resistor, okay, is set to 0 volts, we would get the potential difference across the resistor is also 0, okay, and so the lamp is going to get 2.4 volts, okay, because again it all adds up to 2.4, okay, so that's fine, that's the maximum, okay, it will have. Now, however, you are only going to be able to increase the variable resistor reading from here, okay, from 0 to a maximum, okay. So for that, now the potential difference across the bulb, the lamp, is going to be the remainder of what the variable resistor has. So the maximum it has. So it would be a very, very arbitrarily small value. So I'm going to say over here that when the variable resistor is at 0, the PD across the resistor across it will be 0, and so V across the lamp is going to be 2.4 volts. Okay, but then when the reading on variable resistor, can I just note that? Okay, is increasing or is increased. Okay, the lamp, or the V across the lamp, is going to be basically equal to, you can say, 2.4 minus the voltage across the variable resistor, which is 60 times the resistance times by whatever current is flowing through. Okay, so this is going to be, it's a really weird question, I think. This will be an arbitrarily small value, but because we don't know much about the bulb, the current, etc., it's really hard to say exactly what they mean by small values. Okay, so I'm just going to say that which will be, can't fit in, I'll put it right up there, arbitrarily, I can't spell arbitrarily small. Okay, there we go. Okay, so that's my part I done. Then the next part of the question says complete figure 16 to design a circuit so that the data may be obtained from 4V from 0 to 2.4 volts for the lamp. Okay, so this is more of a potentiometer circuit where you are sliding, the sliding contact, or the rheostat circuit. So if I just start by drawing a resistor, a fixed resistor, and like so, and what I'm gonna do is put a bulb across it. So here is just actually I'm gonna put an ammeter over here so that it's able to calculate the current, measure the current. And then I'm going to put a sliding contact circuit, so let's say you're able to just move it like that, and then across it I have a voltmeter so that it's able to measure the voltage for the lamp. Okay, so that is going to be my circuit, and I can just move from position, let's say, I don't want to label it A, but X to Y. Okay, as you move across, the resistance of the resistor will increase. Okay, and so you can vary it from 0 to 2.4 volts for the lamp easily. Okay, so that's part I done. Let's move on to question number 17, where we're given that students are given a glass block and a ray box to determine the refractive index of glass. The students measure angle I and R, and the results are shown below. The refractive index of air is 1. Describe with the aid of a labeled diagram how the students may have conducted experiments in the lab. Discuss how you could use the data from the table to graphically determine a value of the refractive index of glass. So for questions like this, I always like to work backwards. Okay, so because I know I need to work out the refractive index of glass, and I am given the refractive index of air, I will use Snell's law. Okay, so Snell's law, so this is just a bit of background information. So I know that it is N1 sine I is equal to N2 sine R. Okay, worth remembering if you don't already. Now, this is already 1. Okay, so this sort of disappears. And so if I want to work out the refractive index of glass, so this is my refractive index of glass, okay? And so if I want to work this out, I can simply just rearrange to say it's sine I over sine R, okay? And that is therefore, I'm going to have to draw a graph of sine I versus sine R, okay? And basically it would be a straight line passing through the origin, or even if I, you know, I could start from 10 degrees over here, etc. Yeah, basically I would end up getting the gradient as my refractive index of the glass. So that's the idea. And you can, of course, draw the error bars for accuracy to work out the uncertainty. So now how do I conduct this experiment? How do I figure out sine I and R? Well, for that, so let's just put this on at the bottom so that I can actually use it to further explain. Oops, I don't have enough space. Let's put it over here. I'll get rid of it if the need be. So we are going to use a, let's say an A3 paper, okay, white paper. And on top of that, we are going to place a glass block. And there we go. And we're going to use a ray box or a lamp with slits, whatever works. Well, we are given, yeah, it says we are given a ray box, so we're going to just use that. And we can use a, gosh, my drawing is horrible. So we can set it up in such a way that we are able to, let's say it's really bad, but can I delete it? Okay, let's just do it at an angle. That's better. So it is making a ray incident on the glass block, and we can start with an angle of 10 degrees over here, okay, which is the angle of incidence, and then it would basically refract outwards as, oh no, it would refract inwards, okay, and because it slows down, so it would, the angle is smaller, yep. So this is not the greatest diagram, but you would end up basically getting something like that. That's better. And you are then going to measure the, you can put a mark with a pencil, okay, where you see the ray coming out, and then you will be able to measure the angle as you just, with respect to here, okay, this bit over here will be your angle of refraction. Okay, so that is an easy way of doing it. You can outline the glass block and remove it so that you are able to measure it using a protractor. So I'm going to just write these points down. Part B, we are given figure 17, shows a ray of light at the boundary between glass and water, and describe how the wavelength of the light changes as the light travels from glass to water. So from glass to water, it is going to speed up, okay, because it is obviously less dense. So as V is increasing, lambda would also increase, okay. For question number 18 now, state the meaning of coherence. So coherence is basically when you have constant phase difference and same frequency. So same frequency. Okay, part B. Figure 18 shows a loudspeaker placed in between two narrow slits in a metal plate. And the loudspeaker emits sound waves of frequency 2.8 kilohertz, and the separation between the centers of the narrow slits is 0.4 meters. A microphone moved along the line XY at a distance of 5 meters from the slits detects region of low and high intensity, of course, okay. The separation between the adjacent regions of low and high intensity sound is 0.75. Okay, that's important. Let's just highlight that. And then explain how you can use an oscilloscope set to a time base of 0.1 millisecond per division to check that the frequency of the sound is 2.8 kilohertz. Okay, so all you have to do is basically measure the peak to peak, peak to peak number of divisions of the wave signal generated from the loudspeaker. Okay, connected speaker connected to a signal generator, an oscilloscope, and then in order to measure the frequency to be 2.8 kilohertz, I could just do 1 over to cheekily work out on the side what should be the time period, so how many divisions there should be. So 28, okay, 100, and that is gonna be equal to 3.6, 3.6 times 10 to the minus 4, 3.6 times 10 to the minus 4 per second. Oh, sorry, second, my bad. And obviously this is 0.1 milliseconds. Okay, so there would be therefore 3.6, yep, 3.6 divisions. Okay, there should be 3.6 divisions because obviously this is in seconds. Okay, so there should be 3.6 divisions as each one is 0.1 millisecond. Okay, so let's move on to our next part, which says explain how the arrangement shown in figure 18 produces an interference pattern along the line XY. So let's go back up. Okay, so we know that as the loudspeaker is producing sound, the two slits will cause diffraction to happen. And because of the diffraction along the two slits, okay, I can never draw really well, but you probably get an idea. There would be constructive and destructive interference taking place, or maximas and minimas forming when the waves are going to meet in phase or 0 degrees phase difference, and when it's destructive interference, it will be out of phase, okay, 180 out of phase. So that's when the intensity is going to decrease to 0. So that's what I'm going to say over here. For part I, calculate the wavelength of sound. Okay, so we know that wavelength is equal to AX over D. Okay, so we are given a bunch of numbers right up here. So I'm just going to get rid of this atrocious drawing. Okay, so we're given the value of A, which is the distance between the slits, as 0.4 meters. The distance between the slit and the screen is given to us, and the adjacent low and high intensities are given to us as well as 0.75. Now, this, therefore, is the difference, okay, 0.75 is the difference between maxima and minima, right, or minima and maxima, okay, which means that it is going to be double. The wave, distance, sorry, between the two maximas are going to be therefore double of 0.75, okay, because the value of x, or what x stands for, is the distance between two, okay, two adjacent maximas, okay, so it's going to be therefore 2 times 0.75 meters, and now when we put in all the numbers, we will end up getting an answer of 0.12 meters. Okay, then we have to calculate the speed of sound. That's easy peasy. V is equal to F lambda. F is 2800 and lambda is 0.12, which gives me 340 meters per second. For part V, State and explain the effect, if any, on the position and the intensity of maximum. The amplitude is halved. Okay, so we know that intensity is proportional. Intensity is proportional to amplitude square. Okay, so if the amplitude is halved, the intensity will decrease by a quarter, by a fourth. Okay, or by a factor of 4, decrease by a factor of 4, I mean. Okay, so however, the positions don't change. Okay, positions won't change, as intensity has got nothing to do with x. Okay, so x is proportional to lambda, okay, directly proportional to lambda, or d, and inversely proportional to a. So it's not going to affect the positions of the maxima. Okay, question number 19. We are given that a photo cell is in figure 19, where metal M is exposed to electromagnetic radiation. Photoelectrons are ejected from the surface of the metal. These photoelectrons are collected at the electrode C, and a sensitive ammeter indicates the presence of a tiny current. The work function is so the incident EM radiation has a wavelength of so, and the ammeter reading is 0.24 microamps. Calculate the number of photoelectrons reaching C in time of 5 seconds. So we know the photoelectrons, which is basically the current, is involving the charge and the number of electrons. So Q is equal to NE, we know that. And we also know that Q is I times T. So if you want to work out essentially N over T, okay, N over T, it's equal to I over E, okay. In fact, sorry, I should probably times it by T. Never mind, because it's just not number of photoelectrons per second, it's more like number of electrons in 5 seconds. So let's just get rid of that over here and have it as that. That's better. So we have all our numbers, okay, in the correct units, and we end up getting an answer of 7.5 times 10 to the power of 12. Okay, part B. Calculate the maximum kinetic energy of the ejected photoelectrons. We know that HF minus the work function is equal to EK max. Okay, so H is known, and as well as the frequency is can be calculated using C over lambda, because I know we are given the lambda as this. Okay, so let's put that in to the calculation. That's to the power of 8, and 5.1 times 10 to the minus 7 minus the work function, which is given to us as 2.3 EV. Must convert this into joules, so times it by this term, and yeah, whack it in the calculator, and you'll end up getting 2.2 times 10 to the minus 20 joules. Okay, part C. It says the wavelength of the incident radiation is kept constant, but the intensity is doubled. State and explain the effect, if any, on the current in the photo cell. Okay, so the rate, because the intensity is doubled, okay, that just means that the photons per second, okay, incident, okay, I'll just change that. So the number of photons incident per second increases, okay, on doubles. So the current, which is basically the photoelectrons, okay, will also double, okay. As in the current is the speed, right? So yeah, current would also double. Okay, cool. So let's get on with question number 20 now. State what is meant by the decay constant of an isotope. Well, it is the probability of decay of a nucleus per second. So nice and simple. So next question says that a radioactive substance has 2000 nuclei and the decay constant of this isotope is 0.1 per second. Use this equation and delta T as 1 second to estimate the number of nuclei left after 2 seconds. So let's find out delta N, so after 1 second, so minus lambda N times by delta T, which is minus, we can remove the minus sign actually because we're just working out the change in number and we know that it's a decrease. So 0.1 times by 2000 times by 1, which is 200. So after in t equals 2 seconds, you're going to be now left with 1800 nuclei. So delta N now will be 0.1 times by 1800 times by 1, which is 180. And therefore, after 2 seconds, it's going to be 1800 minus 180, which will be left as 1620 nuclei. So for part C of this question, it says a group of students are investigating the decay of protactinium, and a fresh sample of protactinium is prepared. The activity was measured at the intervals of 1 minute for 6 minutes, and figure 20 shows a variation of ln A with T. Okay, that's here. Now we need to figure out, explain how the graph can be used to determine the half-life of protactinium, determine the half-life of this nuclei, and include an uncertainty in your value. Okay, so we have to understand how we can link this to determine the half-life. How can we link the graph to determine the half-life? And to begin with, I know the equation, which is given to us as A equals A naught e to the power of minus lambda t, okay, where A is the activity, A naught is the original activity, lambda is the decay constant, and t is the time. So now on here in this particular graph, we are talking about ln. Okay, so I'm going to use ln A of both sides, and it's got a bit of maths to it over here. So whenever you take ln of both sides and the two functions multiplied, you are going to add them. Okay, and because you have sort of e to the minus lambda t, it would just reduce to minus lambda t. Okay, so now this equation is useful in the way that we can figure out what's in comparison to this graph where t is on the x-axis. We know that m is the gradient. Okay, m is the decay constant. Okay, and so we can use. We also know that half-life is given by ln 2 over lambda, right? So that means that if we calculate the gradient, okay, calculate the gradient of the graph, which will be equal to lambda, okay, and we can figure out the half-life by doing ln 2 over lambda. Okay, so let's work out the gradient of this graph by considering line of best fit first, and I'll try to pass it through as many points as possible. So let's see, so let's start from here. Okay, so this passes through 4 points, and whereas that, okay, I think this is the better fit. Okay, so there's another point, I forgot about that, I didn't see that. Okay, so there's that point. Okay, so I'm going to draw it like so. Okay, that will do. I'll just change it slightly. Maybe that's better. Doesn't make much of a difference. I'll keep it this way. Okay, so it's easier to read therefore as well. So we have 6.5, 6.5, 6, 7, 8. Okay, so 6.85, I'd say, because it's bang in the middle. So that value is 6.85, and the original value is not 0, it's 3, bear that in mind. And the change in x-axis is 6 minutes. Okay, so the gradient is equal to 6.85 minus 3 over 6 minutes, and that will be 0.642. Okay, and now if I work out the t half, I can do ln 2 of 0.642, which gives me 1.08 minutes. Okay, and then 1.08 minutes, and then we could work out the uncertainty by considering the line of worst fit. Now, I know over here we're not really given the error bars. Okay, so I will try to draw one out, making sure I'll just do it in another color. So let's say I consider this in blue. Yeah, I'll just take it from here to, I want to make sure that it doesn't pass through too many points, or even if it does, I will maybe just extend it. Yeah, that will do. Okay, so here we go. So that is 3.5, and we have the same start, so or even, yeah, I'll take the same start. So 6.85 minus 3.5 over 6 minutes. So that is gonna give me a value of, okay, 0.56. Okay, right, so that is, let's move down here. Okay, so that was a gradient of worst line of fit. Okay, so now from here I'm going to work out the I guess I could work out the value of t half. Okay, so t half is ln 2 over 0.56, and ln 2 over that is 1.24 per minute. Okay, and now from here, uncertainty value in half-life is going to be 1.24 minus 1.08 over 1.08 times by 100. So let's see what that gives me as the answer to be, okay, 14.9%. All right, so that is my uncertainty value here. Okay, let's move on to question number 21, which says that a positive charged particle is traveling in a uniform field. Figure 21.1 shows the particle traveling at right angles to the direction of the field. Describe the motion of the particle in terms of the force it experiences when the field is magnetic. Okay, the force is going to be perpendicular, and it will be following a circular path. Then it says, what if the field is electric? Again, it would be, the force will be perpendicular and to the motion, and then it would follow a parabolic path. Okay, so that's pretty straightforward there. Let's move on to our next part of the question, where it says figure 21.2 shows a uniformly charged sphere of radius r. The electric potential at point X is 1800 volts, and point X is at a distance of 2r from the surface of the sphere. Calculate the electric potential at the surface of the sphere. Okay, so this is more of a comparison or a ratio kind of question. So if you were to write down the potential at point X, then it'll be just Q over 4 pi epsilon naught 3r. Okay, so it is always from the distance is always from the center. And similarly, V at the surface is going to be Q over 4 pi epsilon naught times by r. And if you were to compare V surface over Vx, surface over Vx, we can simply cancel quite a few things out and flip it, of course, as we are dealing with two fractions. And it turns out to be simply 3 times, okay, because everything else cancels out. It turns out to be 3 times Vx, okay, so it would give me 5400 volts. For the next question, it says calculate the surface charge when the radius is 4 centimeters. So Q is equal to, again, I can use the same equation as above, just modified. So Q is equal to 5400 times by 4 pi epsilon naught, okay, and 4 centimeters, which is just 0.04. Okay, so the value of epsilon naught is already given to us, which is 8.85 times 10 to the minus 12. And using that, we could end up getting an answer of 2.4 times 10 to the minus 8 coulombs. Next, the question asks us to calculate the electric field strength at the surface of the sphere, where we know that E, electric field strength, is Q over 4 pi epsilon naught R squared in general. And we already know the charge calculated in the previous part. 4 pi epsilon naught is usual, and the radius is 0.04 squared. So from here, we end up getting an answer of those many newtons per coulomb. Okay, for part C, we are given that a figure, 21.3 shows 2 particles with the same charge but opposite signs. State and explain the magnitude of the electric potential at the midpoint between the particles. Well, the magnitude, okay, so electric potential is the same, right, for both the particles, but they have opposite charges, okay? So it would be 0. The overall electric potential will be 0, okay? Okay, question number 22. It says, state the meaning of induced nuclear fission. Okay, well, induced nuclear fission, is when a nucleus absorbs a neutron and simply splits. Okay, it becomes unstable and it splits. Part B says, explain the role of the moderator and control rods in the nuclear reactor. Okay, so moderator, as we know, is there to slow down the fast-moving neutrons released per fission. Okay, and in order so that we are able to carry out further induced fissions. Otherwise, when the neutrons are moving too fast, the uranium nuclei cannot absorb them. Okay, and so they have to be slowed down. And control rods are basically to absorb excess of neutrons so that we can control the rate of fission. Okay, so that it's not a uncontrolled set of chain reactions which could potentially lead to atomic bombs. For part C, it says a possible fission reaction is like follows, where K is the number of neutrons released in the reaction, and the uranium-236 nucleus is very unstable. State the number of K neutrons released in this reaction. So this is one of the simplest questions. You just have to figure out what is the total here, okay, versus the total here in terms of the mass. And there is a deficiency of 2, okay, so K is therefore 2. State the binding energy of the released neutrons, okay? They will be 0 because they are neutrons. Binding energy is that of a nucleus, where it is the energy required to completely strip off a nucleus of its nucleons, okay? So this is neutrons itself, therefore it would be 0. For part III, it says a nuclear reactor uses uranium-235 as a fuel. The output power for the reactor is 1 gigawatts. The mass of uranium-236 is that much, and the mass of the products in total is that much. Calculate the number of fission reactions per second. Okay, well, we know, so we have to think in terms of power, energy, and time. Okay, so first of all, what I'm going to do is work out E equals mc squared, or well, delta E equals delta mc squared, okay, in joules. So it is the mass of the parent nucleus, which is 236.053, okay, minus the mass of the products, which is 235.84, and I would times this whole thing by 1.66 times 10 to the minus 27 to convert it into kilograms. And then I would also times it by the speed of light squared. So that would give me a really small value of in joules, okay, of energy. Now, if I want to work out the number of fissions per second, I am talking N over T sort of thing, okay, which is power over energy, because power is joules per second, okay, and energy is in joules. So ends up being just per second, okay, number per second. So we know that power is gigawatts, so 10 to the 9, divided by the energy, which we calculated right here. So just dividing by that, and it ends up giving us a fairly large number, which is 3.1 times 10 to the power of 19 reactions per second. So let's move on to our question number 23. Part A says, describe the X-ray attenuation mechanisms of simple scatter and pair production. So again, for medical physics, they tend to ask you very textbook-like questions, okay? Simple scatter is where X-ray photons are basically scattered. X-ray photon is scattered by an electron, an atomic electron, okay? Whereas pair production is where X-ray photon basically produces a pair of an electron and a positron, and in that process, it basically disappears. So for part B, we have to calculate the maximum wavelength of the X-rays for pair production process. So as we said, an X-ray photon turns into an electron and a positron. Okay, so one photon, the energy of the photon, is equal to the energy of those two particles, okay, electron and the positron. So I'm just going to call it E naught, okay, rest mass energy is also sometimes what they give this name as. So energy of the photon is hc over lambda and 2mc squared, okay, mass times the speed of light squared. So if I want to work out the wavelength, then lambda is equal to hc over 2mc squared. In other words, if I cancel out the c, it becomes a little bit more straightforward, and I end up getting my answer as 1.2 times 10 to the minus 12 meters. Okay, for question number C, it says an X-ray image of a patient's arm is required. Figure 23.1 shows a parallel beam of X-rays is incident on a cross-section of a patient's arm, not parents, oh my god. And then we are given a graph which is intensity versus the distance x from point A. All right, and we need to explain the shape of this graph. Okay, so this is rather simple. So for the shape, we can see at first up to from 0 to 3 centimeters, which is basically the muscle. Okay, muscle, as the depth increases, the intensity is decreasing linearly at first because it's the same tissue, muscle, right? But then it decreases exponentially as it enters the bone, okay, from 3 centimeters to 4 centimeters. The decrease is sharp at first, and then it slowly slows down, okay, which basically just tells us that the attenuation coefficient of the bone, okay, between 3 to 4 centimeters is higher, okay, as there's more absorption of the X-rays. And then from there, it just slows down as it goes again into the muscle, which is, as with depth, it would, of course, decrease. Okay, the intensity would decrease further. Okay, well, this is the end of the paper, and I hope you found it useful. Let me know in the comments below if you have any questions. I'll see you guys next week with another paper. Thanks ever so much for watching.